Okay, so morning to all of you. What today we are going to take up is design for testability. Till now, we were only talking about combinational logics and sequential logics, and how would we test it, if there is a fault. Okay. Now, what happens is, that is with VLSI circuits, that is becoming very difficult. If you don't include some design elements in the testable elements in the design stage itself, right? So while designing the circuit itself, let me increase the size of the mouse also. So while designing the circuit itself, if we can incorporate a few elements that will make testing easier, then life becomes easy post fabrication. Okay, and that is the reason that aspect is known as design for testability. Okay. We introduced two new terms. One is known as observability and one is controllability. Observability is the ease of observing a node by watching external outputs of the chip. Once the chip is fabricated, if you are able to see the output of any portion of the circuit through an output pin, okay, that is known as observability. Controllability is the ease of forcing a node to 0 or 1 through the input of the chip, because once fabricated, we only have access to the pins. Okay, post fabrication, we can't put a probe inside the nets. Okay, so how those nets are accessible from the pins. Okay, so that defines the observability and controllability. So combinational logic is usually easy to observe and control, whereas sequential circuits may require many cycles that we have seen. But how even the sequential circuit can be made very simple using a scan technique is what we are going to learn today. Right. So like when we are designing two blocks like this, okay, so this is known as ad hoc test. Okay, so when there are two combinational blocks are being fabricated like this, if it is fabricated, generally we'll have input pins right here. If you don't incorporate any design testability elements there, then you will have some input pins. So I can say I can control this block and I can observe this block. Okay, but this block cannot be controlled and this block cannot be observed. Okay, so in both cascaded only we can find what are the faults and things like that. So this is not a very good solution. So we can probably in between the blocks, and we can put one block. Okay, one indicates an OR gate and AND indicates an AND gate, normal AND gate. And then I can have two additional pins to control these gates. Okay, so now if I give CP as 1 and this as 0, then this block 1, so this AND gate becomes transparent. Output of block 1 will be available here. This is 0. So I get the normal mode of operation. Okay, so this additional hardware and these additional pins we are inserting in the chip. Okay, so obviously there is a trade-off between area and number of pins, but then we are making by putting and then by putting an 0 here and putting an 1 here. Okay, I can force a 1 into the B block. So this by putting a 0 here, B block will be isolated. Correct. So I I can force a 0 here. So I can control this B block. I can give a 0 input here, and similarly, if I have to give an 1 to this B block, I can give 1 1. So 1 1 also give you. So by putting these two blocks additional and these two, I can give either an 0 or a 1 to the B block. So B block, the second block. So the second block also becomes controllable. Obviously, we are not observing this block, but you can say that if you can independently verify B block, the second block. Okay, first, okay, if it is working fine, first we do the testing of B2. If it is working fine, then we can do the testing of B1. right? So if this is fine and this is fine, obviously you can say this is also working fine, right? So there is no real requirement of observing this, okay? But once in this case, so we don't know which block is wrong, but in this case we can for sure say which block is wrong, because you can independently first verify block 2. Same thing, instead of an AND and OR gate, we could use an MUX and control this MUX, okay, through this one control signal. I can route an output of block B1, or I can use this, okay, this signal. So this is coming from the pin. So this pin can be on this pin I can give either 0 or 1, okay? So I can do the testing. So these are the two additional blocks at the design stage. When I am designing the circuit itself, I put these two blocks in between, so that post fabrication it enables me enables testing, okay? So these are okay. Now all these things were for small circuits, okay? When you have a small VLSI circuits where the number of blocks are limited, so such things can be done easily, okay? Is it okay with all of you till here? Okay. So for a big VLSI circuits, and we will see a boundary scan technique will be used, but for small circuits, ad hoc design is fine, right? Now if you see here, this output, there will be several blocks, okay? There could be some, say, 15 blocks. Now for an 15 blocks, if I each connected to one other like this, maybe, right? Okay, and if I have to there could be blocks connected like this, whatever. So if I have to verify the outputs of all of them, then I can't take a parallel wire and start getting onto the pins, because once the once a chip is fabricated, right, you have to select the chip before sending for fab. So the number of pins, physical pins, will be limited, right? It won't have infinite number. And then so you can't keep bringing all the intermediary block outputs to one pin, right? So to individual pins, different pins, unique pins. So it will require large number of pins. So what we can do is we can put a MUX. Okay, now this is like if you have, suppose you have 16 different stages, I can have an 4 into 16 MUX. I can have 4 control lines, and using these control lines, one of the signal, required signal, can be routed to the output. Okay, so now obviously it divides, it significantly brings down the number of pins which are required. The disadvantage is obviously only one output can be seen at a time. Okay, otherwise if each output is brought out separately, then you can see multiple outputs at one go. Here only one output can go. Okay, so is it okay till here? Yeah, Ranjani, is it okay? Shall we move forward? Okay. Right, and then we can have instead of an again here also, like if it is 16 controllable signals which needs to be observed, for a MUX will require 4, right? So to log 2, whatever is here, log 2, those many lines are required. So instead of that, we could have an counter itself. Okay, so suppose we initiate this counter, okay, and then let it run at a specified frequency. So we need to design this counter, and when we start the testing, okay, after giving the test vectors and the results are available, once the results are available, then you can trigger the counter, okay, starting from 0 0, and then it's move for. So all these signals one by one it will keep coming out. So and a log can be, all this data which is coming out can be captured and analyzed in later. Okay, so now the advantage out here is only single pin is being consumed here. Okay, and that pin is just to start the counter, and probably one more may be required to stop it, and once you give the stop signal, okay, or you can design it the same signal. Okay, once the signal goes high, the counter starts from 0 0, and when it comes to 0, it will reset to 0. Okay, that internally we can design a digital circuit that way. So automatically it gets a reset to 0. Okay, so that aspect can be taken care of. So only one pin will be consumed out here, and one pin will be utilized for the output. So this is one option. Okay, so these are the advantages. Okay, number of pins can be. And on the input side also, a similar thing can be done, right? Because to give the test vectors, right? So there could be several blocks, and each might require one test vector. So from there we can have an, like, this is a mux which is placed out here. Okay, in the test mode, okay, this signal will come from this output of the demuxer. Okay, now there could be one more block also, right? And block 3, and there will be an mux there. In normal operation, and the output of this will go the block 2. This is block 3. So normally this output also will go there. Normal operation, there will be a mux in between. I don't know. There will be a mux out here, and from the mux it will go, and in the test mode this mux will get an output. So this can come from the second here, right? From the second here. Now similar, because each block some test vector needs to be given, right? So now this is the test vector. Now this is only a single pin catered for to provide the test vector. So how to route this particular pin to different blocks? So this mux is only taking the test vector and or routing the test vector or the previous block output here, but this test vector itself needs to be routed to different blocks, right? So I have one more demux out here, right? And that demux can again be done with a counter. Okay, now this counter needs to be properly synchronized, okay, with the system clock. Only then this entire process will work fine, right? It should not so happen that when I am giving a counter value of say 8, so this 8th output is going to the 8th block, and at the output also the counter is reading 8, and the output is available from that particular block only, right? So this counter of at the out, which is multiplexing the outputs, and the counter and the demux out here, they have to be in sync, right? Otherwise it could happen that you are applying test vector in one place and you are taking the output from some other place. So those errors, so this synchronization of these clocks and counters is important out here, right? So that is okay for small circuits. But for large VLSI circuits, we have something known as a scan design. Okay, so normally we use a normal we learn the advantages of pipelining, right, in our advanced VLSI design. So generally these days, all the processors, you will have a combinational block and a flip-flop, then a combinational block. This is a flip-flop. Okay, this is a pipelined structure. Okay, normal. So most of the processors work on a pipelined architecture. So where you have you don't have big chain of combinational logics, but you will have small bits. All the combinational logics are broken down into a small small chain lengths, and in between we insert flip-flops. The same flip-flops we will now operate in two modes. Okay, one is in the test mode and it's in the scan mode. So this is the normal flip-flop which we studied in our VLSI design class, and that has been modified with a multiplexer in the input side. So when the scan signal is high, so the scan input would be routed to the flip-flop, and in the normal, okay, when this is 0, then the D will be routed to the flip-flop. Okay, so this is an additional modification which we incorporate in the design stage itself. Okay. Now what happens, see the advantage, it is first of all, in the normal operation, and okay, all of them will normally take this output and go, and during the scan operation, now this output of the flip-flop is going to this combinational block, and also it is coming here. Okay, that is why it is known as a scan. Okay, so this is coming out here, and this is coming out here, this is coming out here. This is going to the next. So all these flip-flops will be connected as a chain. Okay, so only one pin is required to scan in the data, and one pin will be required to scan out the data. So first I put it into the scan mode, and I put the test vectors out here everywhere. Okay, so once I put all the required test vectors, then I put it into the normal mode for 1 clock. Then once I give it in the normal mode, when I am putting this scan data, this is also computing, okay, because this data is parallelly available. But once this data is settled in these flip-flops, I give it to the normal mode. So the moment I put it into the how do I put it in the normal mode? Through this multiplexer signal, right? So this data, so this flip-flop will capture this data. Okay. The moment I put it in the normal mode, the output of the combinational logic will be captured by all these flip-flops, right? So all this data, this will be given here, obviously, output of this will be given here, right? This output will, so all this, once the clock is given, this new data, with one clock, this new data will be captured. Again, I put it back into the test mode, and again, these are, since they are sequentially, we'll shift out and get all the data out here, right? So is this thing clear to all of you? Yeah. Okay. Tell me what is the greatest advantage seeing this circuit just by having these scan. Okay, from what we have studied some testing of combinational logic, we have studied some of sequential testing, right? So now we are seeing it can be done like this. Okay, so what appears in your mind? What could be a great advantage here? Anybody? Yeah, Gokhale, Jaising, Kirti, anybody?
Sir, only very few pins are required. It's a complete big serial chain.
Pin count is reduced, sir.
Yeah, pin count is reduced. But what were the problems in sequential
Parallelly
testing?
output also can. Sorry.
What was the problem in sequential testing as compared to the combinational? When we studied about sequential testing means when there were flip-flops also involved in the circuit. What was one of the major problems there?
Initial conditions?
Wait for many
correct. When they were when it was sequential circuits, you had to initialize them, right, through giving. So so many test vectors were required. Some of them were in right connected in cyclic form. So we required 2 test vectors to put that initial condition into those flip-flops and all, right? Now this problem, okay, has become simple, right? It is just pure combinational circuit. We right, all that, although it is a sequential circuit because there are flip-flops involved, but we are able to somehow put data into those flip-flops through the scan data. So the problem statement has now become pure combinational, correct? Because initialization is no more a problem out here. Okay, so that is an great advantage. Okay, now we'll see so how does this flip-flop look like? So this is a master slave flip-flop. Okay, So here instead of a master slave flip-flop, initially a mux has been incorporated out here. So here TC is the test control, and it is an active low signal. Okay, active low signal means when it is 0, then it is in the test mode. So when it is 0, obviously this D input is isolated, and the scan, and this is scan data, this is activated. So the scan data will be made available to the flip-flop, and when T is equal to 1, since it's active 1, so test control will be deactivated, test will be deactivated, and D will be available. Okay, so this is the circuit. Okay, so this is the modified circuit of a flip. These are the kind of flip-flops which we are going to use now. So most of the modern processors, it will be the flip-flops will be like this. Okay. So this is one design where the mux has been incorporated out here. Okay, one disadvantage will be the delay for the D. Okay, so the total delay and setup time, things like that, will be slightly bad out here, because one mux has come in between, right? So you could have this configuration also. Here like they are in parallel out here, right? So here this is the master clock, this is the slave clock, and this is the test control. So if you have this as high, right, and you have the test control as low, right, in this case, so this will be isolated, right? Then D will be sent. This will work as a normal thing, right? And in the scan mode, this will be the master control will be held 0. Okay, so this output is not there, and the this will be placed high. Now the scan data will be given here. So this NOR gate has been modified. Instead of an 2 input NOR gate normally we have, now that becomes an 3 input. So this is now these two circuits are placed one above the other. So this is for the D, and this is for the scan data. Okay, now the advantage out here is during normal operations, since they are not in series like this. Okay, so there is no additional, there is no penalty on the performance. Okay, in terms of speed of operations and setup time, and those things don't get modified here. It is a norm. So this is another option which we have. So one of these options will be used. Right, this is like okay, all the flip flops. There is a combinational logic, and for each of the outputs, and you will have some scans, and these flip flops. These are additional routing which will be done. These flip flop, not only this output will be available in the flip flop and to out, also these flip flops needs to be interconnected, right? Because when we are scanning the information, then this combinational block won't be there, but all this scan chain should be activated. Similarly, once the test is done, the scan chain is activated to bilk out all the data through a single pin. Okay, so there will be a one scan in pin and one scan out pin, and this is known as scan flip flop. Okay, so that this flip flop is known as scan flip flop. This is right. The certain rules are to be followed when we are designing for testability. The thing is only a master slave, D type master slave flip flops should be used. Okay, the moment we have JK, toggle, or other flip flops, then this scan design won't work. Right, so it is important that when we are making a sequential design, we use only a D flip flop. Initially, we like when we start designing the circuit, we will just use D flip flops, and subsequently we will modify those D flip flops into scan flip flops, right? But in the design stage, if you are incorporating JK, toggle, and other flip flops, then the scan input won't work. Okay, because for scanning only from one to other, okay, the D the Q will become the D of the next stage. So, but if it is a JK flip-flop, then it becomes difficult to scan data into those flip-flops, right? So we can't use JK flip-flops. Okay, so that is. And the second one is at least one primary input pin must be available and one output. So from the pin side, there will be several pins. At least one pin should be connected to the first flip-flop. Okay, that could be through a mux also. It need not be a totally independent pin also, because we are not going to use that in normal operation. It can go to the combinational logic, and during test it can, because test and normal operation simultaneously we won't be using that pin. Okay, so at least one of the input pins should be available for the scan function, not exclusively available for scan function, through a mux also. So that pin can in one mode act like an input pin, in the other mode we should be able to use it as a scan in pin. The same holds good for the output. So in the scan out mode, that pin we should be able to use it to read the data. Otherwise, it could give some primary output. Okay, these are the two rules. And then the third rule is all the flip-flops should be synchronous in nature. You can't have gated clocks like this in your design, right? If this is the case, then we will not be able to easily put the scan data or read the scan data out. Okay. Now here, if you see here, this D1 is going to this flip-flop. And the clock is gated out here, so the clock will be available only when D2 is high. Okay, so this will cause a failure in the design rule. Okay, so instead of that, we can have the same thing modified out here. Okay, the functionally this circuit and this circuit will be the same. If there is a requirement to do like this, right? There could be a requirement, like when you are probably when you are designing a counter. Okay, if the MSB count needs to change only when the LSB is 1, right? From 0 to 1 only the LSB changes, but when the LSB changes from 1 to 0, then the next MSB changes. So in those cases, there might be a requirement like this. So this particular circuit can also be implemented like this. If you see here, when D2 is 0, okay, when D2 is 0, this gate is disabled, right? And you have an OR gate, and this Q is available. When D2 is 0, okay, and this gate is enabled, and you have a Q coming here, right? So it will continue to hold a Q. So that's what was the requirement here also. When D2 is equal to 0, no clock is coming here. No clock is coming here means the Q will continue to be retained here. Here also we are doing that. Okay, here the clock itself was gated. Here we are making available the clock here, but it is again rewriting Q into the system. So there won't be any change in the value. And here when Q is equal to 1, so new value of D will be captured. The same thing happens here when D is equal to 1, the top gate is disabled and bottom one is enabled and gate, and whatever is the value of D will be captured. So these two are functionally one and the same, but this is okay for testability, right? So this kind of, if there is a requirement of some circuit like this, that should be implemented in this manner, where everything works in a synchronous fashion. A synchronous fashion means each will be triggered by the same clock. Okay, so that is the one other requirement. Now okay, now to do the testing, okay, first we need to test whether these flip-flops are working fine or not. Okay, if I go back out here in the scan design, okay, the first is, okay, before I test the combinational circuit, okay, I will test whether these flip-flops are working fine or not. Okay, and for that, what I do is I send a test pattern here, and I read a test pattern out here. Okay, and whatever, if I am sending this test pattern, if I am able to read here, okay, then I can say in the scan mode, can I say all these flip-flops are okay? Yeah, Jason? Okay, I'm connecting it in the scan mode first. Okay, and in the scan mode, I'm sending in some data out here. Okay, I'll keep pushing some data here and keep reading data here. Okay, all these combinational blocks are bypassed. Okay, in the scan mode. So in the scan mode, I'm doing that. Then I'll read this data here. Okay, then I can say, okay, all these flip flops are working fine, and then I will go for the combinational logic test. Okay, so in the scan design, like earlier, we thought by putting these things, and we are only trying to find out whether the logical combinational logic is good. No, that's not the case. Actually, we can also do the testing of these flip flops also. So you see, as compared to our even when we did the sequential testing, okay, we there assumed that the flip flops are working fine. Okay, so but here you see this testing is more much more reliable, because even the functioning of the flip flops is being ascertained here. Yeah, okay. If you remember from our testing lectures of sequential circuits, we made an assumption there that the flip flops are working fine, right? And then so that's not the case out here. So we can even run a test to ascertain whether the flip flops are working fine or not. Now, what is the test pattern required? Okay, let's talk about that. Yeah, here. Right, so the test pattern is 0 0 1 1 0 0 1 1. Like we keep repeating this, okay, to test. Now, when I go from 0 to 0, okay, the flip flop flipping from 0 to 0 will be verified. When I am going from 0 to 1, next pattern, okay, then my flip flop changing from 0 to 1 will be verified, then 1 to 1 will be verified, then I am repeating this 0 0 1 1 again once more. So if I repeat it again, 1 to 0 transition also will be verified. Okay, so how many test vectors and how long should I run this? Okay, so that the questions. Now if the number of flip flops is Sn, then n plus 4 input, this should repeat it in the input side. Okay, the total number of bits out here, okay, should be n plus 4. Okay, the length of this string. So n plus 4 clocks will be required, and this is the string. It will start with 0 0 0 1 1. Okay, into those many number of flip flops. Okay, plus 4. Okay. Now let's talk about two flip flops and see whether what I am saying. Suppose there are just two flip flops. Okay, I am giving an input. Initially, both were x. Okay, both were x. So in the first clock, I'll put a 0 here. So this is x. Okay, I'm reading the output out here. So in the next clock again I give 0 here, so this 0 will come here. Now in the next clock I am giving a 1 here, so this 1 no, this will be 0 here. Again I will give a 1 here, so this will become 1 here. Then I give another 0 here, so a 1 will come here. I give another 0 here. A 0 will come here. Okay, so this is the in 0 0 1 1, right, and then again 0 0. So if it is only 2, right, then the total number of thing required is n, because there are two flip flops, 2 are required here, plus 4. Okay, so only 6 are required. Now why only 6 are required? If you see here, for this flip flop, okay, 0 0 transition has happened, 0 to 1 transition has happened, 1 to 0 transition has happened, all the 4 transitions are happened, and for this flip flop also 0 to 0, 0 to 1, 1 to 1, 1 to 0. So at the end of when I'm reading, this is the first clock and this is the 6th clock, and in the 6th clock when I'm reading, if everything is coming in order, that means both the flip flops for all the 4 conditions have been checked. Okay, so is this formula, logic of this formula clear to all of you? Yeah, Gokhale Jason, is it okay? Kirti?
Yes, sir.
Okay,
Yes, sir.
so this
Yes,
is the total number of clock cycles which will be required, okay, to check. Now having done that, after that we need to check the flip-flops, okay, the combinational logic. So so we'll load the combinational circuit, right? So say suppose there is several combinational circuits are there, okay, all the combinational there is one combinational circuit here, one combinational circuit here, right? So say for one particular test vector for each combinational circuit, this is one combinational circuit, this is, so so there could be so many combinational circuits out here. Let me go back to this figure, I think this is better. Now this is a combinational circuit, this is a combinational circuit. Now I want to place one test vector, okay. So how many clock cycles will be required to place the test vector? Can you make a guess? I want to give some test vector, right? It could be for this combinational logic, it could be say T0 to Tn, okay. Here also it could be say T0 to some. So how many clock cycles will I require to place the test data? N clock
Sir,
cycles.
first,
Eight required for flip-flop, 2 required for combinational.
Yeah, no, first
Total 10.
Total 10. No, if I
16
say
flip-flop. 16 are there, na? 16 to 4 plus 4, 8 and 2.
which 4? These 4, is it?
For flip-flop.
No, no, I'm not talking
no.
about the
Already loaded?
First we have done the flip-flop testing. It's done and over. Now
Okay.
I want to test the combinational logic, so I'm putting in some test data, okay. Now that test data has to come to all the flip-flops, right? So if there are n flip-flops, so that many clock cycles will be required to bring in the test data to each of those flip-flops.
yes, sir.
Okay, correct?
Yes.
Guessing, is it okay? If
Yes,
there are
yes,
n,
yes,
n,
sir.
okay, after putting all the data there, okay, all the data there, then what should I do? I should again make these mux, I have to put it in the normal operation, okay, and give one more clock, so that result of that test is again captured. So n plus 1, correct? That much will be required for one particular test vector. Is it okay?
Okay.
Okay.
Sir,
Yeah, tell
sir,
me.
just one question. So here actually, I mean, why we have to put normal input? Because now we have like all the test data is already loaded in like 12 flip-flops. And now that is like already connected to
Yes.
combinational circuit.
Yes.
So
But I need
after
to
like
capture the output of those combinational circuits and then scan it out.
right, okay.
So that one additional is to capture the output, okay, right? And then n plus 1, then again another n clocks will be required to scan this data out, okay. Now also,
Yeah, understood, sir.
each of
Yes.
these combinational blocks might require multiple test vectors, right?
Yes.
This will require, this is only one test vector has come, and you put the data, capture the data and take it out. Again the next test vector needs to be loaded, okay. Another but when we are loading this test vector, this block is being tested with one test vector, this block is also loaded with some other test vector, right? They need not be the same, right? It is just the sequence. So whatever this parallelly, these two blocks will be tested, correct? It is not that and only one, all the combinational blocks will be tested parallelly with some test vector, okay. And those test vectors also need not be the same. It depends on your input pattern. So the total number of testing out here, this is n plus 1, and that is loading of the test vector plus capturing the data into number of test vectors, okay. So it is the number of test vectors you have to do that, and then you have to finally take the these things to the output also, okay, to scan out the results also. So so that is also will be required. So plus you need to do this, okay. So if you simplify this, okay, this is the result which comes, okay. So this is the total number of scan length which is required. Now this is just an example out here, for an modulo 3 counter. Okay, we don't have to get into details of this design. It is a modulo 3 counter. Modulo 3 counter means it will count 0 0 0 1 1 0, and it will come to 0 here, right? Many people get confused. Modulo 3 means it doesn't go to value 3. Okay, modulo 3 means total count is 3. Okay, total number of unique states. Okay, it won't go to 1 1. So this reset is given here, so that it is asynchronous reset. So it will put all these both these things to 0 0. And there is a cyclic circuit out here. This is a flip flop, and so this will sequential normal counter design it has been done here. Okay, so we'll not discuss the counter design, but let's assume this is a counter which is working fine. Okay, so the conditions is r is equal to 0 will r is equal to 1 will reset it, r is equal to 0 and c equal to 1, it will start counting with each clock. It will go from 0 to 0 1 to 1 to 0. And then when c is equal to 0, it will stop counting and it will retain whatever value is there. And then when the output is 1 0, which is the maximum state, at that time the output here I have one more output which will go high. Okay, indicating it is in the max count. Okay, so this is the design of the circuit. Okay, now it is just to show this circuit. So once we do an sequential testing of this, try to do without the scan. Okay, normal sequential circuit, the automatic test pattern generation program generated 35 vectors to cover 36 faults of 42 faults. Okay, 6 faults were not detectable. Because if you see here in this particular circuit, it is cyclic in nature. Okay, so there is a feedback path also available, and hence there were 6 faults which were not detectable, and 36 faults were detectable. Okay, cyclic one. Okay, now for an once we incorporated a scan design, then first what we do, we just remove the flip-flops and consider this as a pure combinational block. So when it was done as a pure combinational block analysis, okay, 12 test vectors were required, right? So because this is we do fault collapsing and we do all those algorithms which we studied. So once this flip-flop was removed and pure combinational ATPG for pure combinational circuit was done, then it generated 12 vectors. Okay, now I incorporated this, if I do as instead of normal flip-flop, I put it as a scan flip-flop, then the total number of tests that will be required, and when we do the 12 test vectors will cover all the faults in the combinational circuits. Okay, so there was nothing which was skipped because there is no flip-flop and there is no feedback path. So 12 test vectors was good enough because many test vectors will cater for multiple faults. Okay, so that we saw fault dominance, fault collapsing and things like that. So 12 test vectors were required. So now if you put a scan flip-flop here, okay, so total number of faults which the test scan test length, if I have to compute, 12 different test vectors are there, plus 2 number of flip-flops are there, and n combinational is again 12. So this formula is nothing but what we calculated here, that is written in a simplified manner here, right? So once it is done, so total test length for testing this, okay, to do almost 100% fault coverage, including the functioning of the flip-flop, okay, 44 is only required, right? Obviously, if you do just a sequential testing, only 35 will be there, right? But out of which only 6 faults go undetected, right? Also, flip-flop faults are not counted here, right? So there is a marginal increase in the number of test vectors required, number of clock cycles required. but you see the advantage of having a scan design. Okay, so no need of remembering the functioning of this example is there in the textbook, just to give you an idea of how beneficial the scan test is all about. Okay, right. Okay, and this is just telling that instead of having flip-flops here like this, individual flip-flops, okay, here you could have a single big register. Okay, so that this routing problem here is a little bit avoided. So you can with obviously registers will have multiplexers incorporated in that. If you remember in our last class, I think in the advanced VLSI class, we discussed about universal registers, right? Where data the parallelly data can be loaded, or serially data can be pushed from one flip-flop to other. So these are we make use of registers as a single registers, so that helps in keeping it simple. So while we saw the advantages of having a scan design, there are certain drawbacks also. So let's discuss the penalty of having a scan design. The first is the gate overhead. So if this is the normal flip-flop, this is a scan flip-flop. Okay, so 1, 2, 3, 4 additional gates have come here. So if I have to tell in terms of the percentage gate overhead, okay, by incorporating the scan into the design, so total number of gates, the extra gate overhead is just the percentage of the extra gates that comes if we modify the normal flip-flop into scan flip-flop. So this is the total number of gates. NG is the total number of gates in the total combinational gates. Okay, so that doesn't change, and this is the total number of flip-flops. Okay, so that also doesn't change. What changes is for the total number of flip-flops, and additional 4 gates come. Okay, so this is 4 into number of flip-flops, scan flip-flops. Okay, so for if there are n number of scan flip-flops, okay, 4 additional gates will come here, right? So this is scan flip-flops. Okay, this is because not all the flip-flops are being converted into scan flip-flops. Okay, so there could be we'll see that. Okay, there is something known as partial flip-flop, so partial scan, where not every flip-flop will be converted into scan flip-flop. We can leave aside some flip-flops which are not really required. So NFFF is the total number of flip-flops, and total number of flip-flops without scan, the number of gates, if you see here, 1, 2, 3, 4, 5, 6, 7, 8, and 2 inverters, 10. So 10. So NG is the total number of gates in the total chip. Okay, and this is the total number of flip-flops in the chip without a scan design, and each flip-flop will have 10 gates. But if out of these n flip-flop, ns flip-flops have, if it is converted into scan flip-flop, for each of those scan flip-flops, 4 additional gates would be there. Okay, so this is the total overhead. Okay, so so this is just a figure of demerit, you could call, where this much of additional gate penalty which we have to pay. Okay, the second is area. Okay, so this is normally you have an chip. This is X and this is Y, the chip area, and these are the IO pads. And here the shaded ones are the flip-flops, and the not the shaded one, the ones which are marked with the cross lines are the flip-flops, and these shaded ones are the combinational logics. Okay, now when we modify it with a scan design, each of this flip-flop, if you see here, now it's going to take some additional space. Okay, so this width is, and this width, if you notice, this is slightly more. Okay, that is because now additional 4 gates are also there here. And also here if you see, there is a routing requirement. Here some additional this flip flop is being interconnected. So although that additional routing the test control line and additional routing requirement is there. So this area will be from here to here. This area will be slightly higher. Okay, so now this is a small mathematics given out here, so it's not important from your exam point of view. So but let's just try and see on what is the area penability. Okay, so x is the this x. Okay, it says c plus s divided by r. Okay, c is the width of the combinational and s is the width of the flip flop. Okay, so if I go back here, c is this width. Okay, combinational width, and s is the width of the flip flop. Okay, normal flip flop out here, this width. Okay, but c is the total width of all the combinational circuits in the circuit, and that's how it is defined here. Okay, combinational width of combinational combined width of combinational cells. So if there are 100 combinational cells, the total width is C, capital C. And similarly, if there are 100 flip flops, the total width is S. Okay, combined. Okay, so each is right. So this is the combined, and you have C, and then they are placed one above the other in n rows. Okay, so they are placed in n rows. Okay. R rows. Okay, R rows. So you divide by R, then you get the total width of the chip. Okay, is this calculation okay with all of you? Yeah, is it fine?
Yes, sir.
Okay.
Yes, sir.
Now when I say if I am going with a scan design, this I have introduced here one more alpha. So if you see, alpha is the fractional width in increase of the scan flip flop over non-scan flip flop. That means if I am replacing this with an this flip flop with a scan flip flop, okay, then this much percentage increase will be there. Okay, this much a fractional increase. So I need to add that. So now this x dash out here is this for the chip with scan design. So x dash will be greater than x, and that factor is given here. Okay, similarly if I have to compute the height. Okay, so the now T, capital T is defined as the cell height in number of tracks. Okay, it is not in absolute nanometer or micrometer. It is number of tracks. Okay, for a cell height. Okay, that means T is the height of the cell. Height of the cell is generally this will be fixed. Okay, for each cell. Okay, when you pick up from the standard library, these cells are generally kept the same. So this is known as capital T. If capital T capital T means it is T into the height of the track. Okay, so in terms of the T unit is track is this small tracks. Okay, so how many? So in multiples of, so this could be 3 tracks or 4 tracks. This height. Okay, so track is the horizontal lines which are running. So that is track height. So number of tracks consumed in this cell height. Okay, that is given as T. Okay, now beta is given the fraction of the active area occupied by the routing channel. So routing channels also, these routing channels, now without the scan design, these routing channels, okay, will also consume space, right? So the total from here to here, okay, if I have to find out, okay, the combined height of a cell row and adjoining routing channel will be T divided by 1 minus beta. Okay, now beta is defined as the fraction of the active area occupied by the routing channel. So T divided by 1 minus beta, okay, is this one is corresponding to one cell plus the adjoining routing channel. Okay, and those many tracks. Okay, those many tracks. Now, so the number of rows, okay, can be computed as v divided by y by t. Okay, so here small y is track width in lengths. Okay, now to compute it in terms of into if I multiply it with y, I will get the in length units. Okay, after, and then if the total y number of rows will be y divided by those many. So you do that, right? And for a y dash, okay, again we are assuming that for each, so there is an assumption which is made that for each row one additional track is being inserted. For each track and addition each this in this area one additional track is being inserted to cater for the scan design. Okay, scan routing. Okay, so that is why that one more factor is put here. So now you get the new y. So you can compute the overhead. This is the new area, this is the old area. So if you try to compute it, okay, you can do, if all these parameters are known, so you can compute this over. Okay, so this is not important from your exam point of view or things like that. Now the only takeaway from this slide should be right. So there will be some additional tracks required. Okay, and that can contribute to some additional area. Okay, so up to 10% area increase can be there because of two things. One, because these flip-flops will occupy slightly more area. Second, the track area also will increase. Okay, because there will be additional routing which will be required to interconnect these flip-flops. Okay, so there are two parameters which will result in an increased area. One is the size of the flip-flop, scan flip-flops itself with respect to the regular flip-flops, and second is the additional interconnecting route requirements. Okay, so these are the two things which will put the slightly result in slightly increased area. Okay, so this is the thing. And the third one is like we discussed earlier also, if you are having a mux out here, so so this D will get captured out here after another additional 2 gate delays. So this can again decrease the slower the clock by 5 to 10%. Okay, because of these two additionals. Okay, so you will see the setup time and the propagation delay. Propagation delay may not be there, but the setup time will definitely be affected out here. Okay, so that will impose an restriction on the setup slack will decrease, and hence the clock needs to be slower 5 to 10%. Okay, and to overcome that we have this particular design, right, where you have a parallel. Okay, so here you will have to use an 3 input NOR gate. Okay, so that this can be done. Okay, and now how to go about designing and full scan design. So there are different types of DFTs. One is known as the full scan design. Okay, in this what we do is we remove all the flip-flops. Okay, and just to take the combinational circuit. Okay, we just remove all the flip-flops and take that as a module, and like if I go back to this here. Okay, this I will take as a combinational module, this I will take as a combinational module, and I will run ATPG and find out what are the test vectors which are required for this. Okay, so even if there is some feedback coming and all, because all those flip-flops are now externally controlled. Okay, so we can put in the required data in those flip-flops. So we will remove all the flip-flops and then we'll run ATG. We'll run an ATPG and find out all the test vectors. Now those test vectors can be put into the sequential into those flip-flops, and we can do. Okay, so this is known as the full scan design method, right? So we could also so this I think we discussed. Okay, there could be a few issues, right, when we are doing a full scan method. So when we are scanning the data out, okay, so this flip-flop is directly coupled to this flip-flop. This flip-flop is directly coupled here without any combinational logic. Okay, so the data could move very fast. So can it result in some violation? When we are scanning in the data?
Hold time violation?
Yeah, hold time violations can happen. So you have to be careful with that. So when we are running a normal thing and when we are running a scan design, okay, there could be when we are just running the scan design, we have to be very careful that because there could be some hold violations. Okay, and also there could be some setup violations also, because when we are doing the routing, okay, when we are doing the routing out here, right, the routing algorithm, okay, will give preference to the normal functional routing. Okay, because excuse me, scanning will be done only during the beginning of the during testing, right? So suppose it's a built-in test, every time you power on your circuit, the scan might happen, but no, after that it is the functional block, and the performance of the chip is depending on how well it is performing, right? So during the normal routine, so the routine operation takes priority. And when we do the routing algorithm, okay, we tell that, okay, the original netlist routing is more important. So there is a possibility that because here it is shown as a very simple circuit, but that may not be the case with hundreds and thousands of chips and modules. Then in that case, when automatic routing is done, it is possible that the scan routing, okay, is lengthier, okay, because the priority is given to the functional routing. So there could be a possibility that the routing is very large in the scan path. Okay, so in that case also you might want to run the scan clock at a slower than the rated. Okay, so you have to see for that. So post routing, when we do the STA analysis, okay, so that at that time we have to see that if there is any violation, if you are giving the same clock or not. Okay, so these things have to be taken care when we are doing. Now multiplexers. Okay, so we saw multiplexers, right? Here is used here, these mux. So it is a faster multiplexer is generally used. Okay, so here if you see here, what is done is when the clock is low, this node will be charged to 1. Okay, this is charged to 1, right? And now if S is equal to 0, select line is 0, then obviously this line is not there, right? This line is not there, this line is there, this S is 0, so this is connected. So whatever is D2 doesn't matter, because I have a ground here, right? So depending on D1, the output would be 0 or 1, correct? Isn't it? When S is 0, right, I have a ground here, and
Yes,
and this output will be D1 bar. Okay, so and similarly when S is 1 here, I have a 1 here, right, I have a 0 here. Since this is 1 here, this is short circuit. Okay, so this output, so there's no ground here in that case, and now this output is dependent on D2. Okay, this is off in that case when S is equal to 1, D1. So the output is dependent on D1. So you could say this is a dynamic mux where either here it is an you can place an inverter after this, where either D1 gets reflected at the output or D2 gets reflected at the output. You could use an inverter, or within the logic you could so incorporate that it is an inversion is available here. So in the next stage accordingly you can cater for that. Okay, so these kind of mux are used, and not an tip. So if you see here, this mux will not have that kind of delay which is there in the typical mux out here, like this much. Okay, because to implement these mux, right, this is an AND gate, so it is an AND followed by an inverter. There is an inverter out here, so this mux is you see so many transistors are required here, right? Whereas this is an much at the transistor level, this mux is implemented only with 5 transistors, right? And a single gate delay for the mux. So this is and obviously the next thing is power dissipation. So normally right, when we are doing the normal operation, there could be some power, but when we are doing the scan operation, okay, there could be a possibility of more average power, and because when we are doing testing, we are giving some other kind of test vectors. When we are doing logical operations and normal operations, okay, we are giving some other kind of test vectors. So there could be a possibility that there could be some additional power dissipation happening during scan, right? And sometimes in the scan operation, we also if there is no violation of the static time requirements, we would want to scan out the data at a very fast rate. Okay, and we could increase the frequency, and because we are pushing in data into the flip-flops and getting out the data on the flip-flops, and if you are meeting the STA requirements, we could complete that scan in and scan data at a much higher frequency also. So you have to be careful while doing that. You have to keep a note of the total power consumption. It should not exceed the power supply requirements of the chip. Okay, so that is one thing. Now we can have something known as a partial scan also, right? So this is a normal, there is a chip here, there is a combination logic here, flip-flops here, flip-flops here, flip-flops here. So these are the level 1 flip-flops, these are the level 2 flip-flops, and level 3. Okay, we defined these levels earlier also, right? This is getting all 1, 2, 3 are getting only primary inputs. C and 2 have got at least one input which is coming from a level 1. So here also, so I put in a no, this 4 and 5 flip-flop are getting inputs from from a level 1 flip-flop also. So these come
degree you told, sir, last lecture. Degree of flip-flop.
Scan some scan depth degree or some word we used. Okay, something like that. So same thing here. Okay, it's different. This is the third level. Some scan degree or some word we used when we were discussing the scan. I don't remember the terminology. Okay.
Yes.
So this we did, right? So now this we can go for a normal sequential. If you don't want to change all these things, okay, this particular circuit, if this is the total circuit example, so it may not be, if you want to change all these things into scan design, we can do that. Otherwise, if we just go for sequential also, there is not much of a problem here. Okay, now the problem comes when there is a feedback like this. Okay, when there is a feedback like this, then the number of test vectors required will be larger, correct? And also because of the feedback, we cannot be sure that all the tests can be generated or not. Okay, so that also we saw, right? If there is a feedback, then in the sequential testing algorithm will fail, or not all stuck-at faults can be detected whenever there is a feedback. So now if I have a circuit something like this, okay, and I don't want to incorporate a scan at every node, every flip-flop, then one solution is there to just to make this flip-flop and this flip-flop as scan flip-flop. Okay, now if I make this flip-flop and this flip-flop as a scan flip-flop, then independently I can push data into these flip-flops, right? And hence that cyclic feedback is broken. So now it reduces into this particular circuit. Okay, like this primary this input is say independently controllable for me, because this feedback, the moment I make this as a scan flip-flop, I can externally put some test data here, so there is no need of initialization of these vectors. Okay, so this is known as where every flip-flop is not a scan flip-flop, only few selected ones we can convert it into scan flip-flop, so as to reduce the scan. So these are kind of design flexibility which is available. So now the designer has to take a call whether he wants a full or even a partial is good enough. Okay, so partial thing, if this entire circuit there are only a few ones which are giving cyclic flip-flop, and it's not a very large VLSI circuit, in that case you might want to have just a partial scan flip-flop also design also. Okay, so here it says like some tests they did, and by just making some partial flip-flop they were able to do obviously full scan design will give you almost close to 100% fault coverage, whereas a partial one, they said they did some these things, and up to 95% right were achieved by converting only about 25 to 50% of the flip-flops were made as scanned, and they were able to cover 95% of the scan of the faults. Okay, so obviously if you make it full scan, then this will go to 100%, but now so you will save upon the area and space and things like that, so there is a trade-off there. So that depends on circuit to circuit and the design requirements. So this one is partial scan. Now in the last class we also I told I'll revisit this. This is known as scan and hold flip-flop. Okay, so this is the scan flip-flop, and no, we have a hold latch, okay, which is following it. Okay, now what happens is suppose especially when we are doing the delay testing. Okay, when the delay testing, when we are doing delay testing, we are doing the scan-in. Okay, for the flip-flops. Okay, so there will be if there are n flip-flops for all the flip-flops, we will put this in a hold right, we'll put the TC to 0, right, and TC 0 means active low, so the scan data will be put, so all the flip-flops will be loaded with the test vector 1. Okay, vector 1. This is set of vector for all the flip-flop. Having done that, now we have to give a vector 2. So this vector 1 needs to be applied to the combinational block. So once this data is fed, I give a hold signal, right? If I give a hold signal from 0 to 1 to 0, so initially hold is 0. Okay, so this is isolated. So the moment I give it to 1 here, whatever is this test vector which is available from the flip-flop, okay, that will be captured into this latch, and then hold signal will go low. Right now, when it goes low, when it goes high, this new test vector, the first test vector is available here, and that is applied to the combinational logic. Okay, and this hold signal has gone low. Now I can again put TC back to 0 and start scanning in the next test vector. Okay, while the test vector new is being scanned in, right, this combinational logic will settle down with V1. Okay, so no change is being applied to the combinational logic. Okay, because this is the old test vector, and once the entire new test vector is available in all the flip-flops, okay, of the chip, okay, new test vector is applied. Okay, then I give an signal, hold signal high. Okay, and that means the new test vector is applied here. Okay, and after a rated clock period of t, okay, again I will capture this. Okay, and the moment I give the hold signal, I will put this scan mode into normal mode. Okay, but if I put it to the normal mode also, data will not be captured here. So I will capture the data after giving this clock signal high. After this second hold, the duration between this hold and this clock will be 1 clock period. So that after applying new test vector v2, after a time period t, this clock will go high, and these flip-flops will capture the new value. Okay, and it should capture the new value. Okay, if there is no delay, excessive delay in the paths, then the new values will correspond to the our lookup table where the correct values are fed. So you compare that with the data available in the lookup table, and if everything matches, then we say okay, there is no path delay. So this additional latch enables delay testing. Okay, so this is what I was trying to explain last time. But then since this was not covered, so it may not have been clear. So is this a hold latch operation clear to all of you? Is it okay, Ranjani? Yeah, okay. So this is a scan hold flip-flop. This is what first hold is put to 0. This is put to 0, and then TC to 1, TC to 1. Set hold to 1. Okay, now if you set hold to 1, initially we are assuming all the primary inputs are available. The moment you put 1 here, then this new data will be captured here. You put hold to 0. Okay, now when you put hold to 0, this data will be logged here. Then again you repeat these steps. Okay, repeat steps means you put the new data, and after putting the new data, again you trigger the hold signal, and after from the place you are triggering the hold signal, the next clock signal, this should be active 1 clock duration. Okay, so that we know that the final output is that the combinational logic has settled down, taken correctly captured, computed the new value depending on the next text vector within 1 clock period. So from here to here, that distance should be 1 clock period. So that is how. And there is another thing with an additional hardware requirement. All these flip-flops can be a RAM cell. Okay. Now the advantage of having a RAM cell is and with an address. So you could put there is a greater control. Right now the thing is, suppose this is a combinational block. Okay, this combinational block requires 3 test vectors, and this combinational block requires 5 test vectors. Okay, so initially for the first 3 runs, I can put scan data here, scan data here, scan data here. So for the second run and second time, again for the 4th and 5th run, again I have to move all this data through these flip-flops. Right here, there will be some junk value you can put, right, because this already testing is complete, whereas here, right, that testing may not be, so only 4 and 5 runs are meant for this clock. So in such cases, there will be some there won't be economy of effort, right, because every combinational block will be unique in nature. Correct. So so that is the reason. So in that case, if we have access to these sets of flip-flops separately, right, then if I can put data into these flip-flops directly, then it is better, right, rather than obviously doing that means creating additional hardware will be there, but the total testing time requirement might reduce. Similarly, for some delay, you may not want to check the delays out here. I want to check for some additional checks on some parts of the logic blocks. Okay, so if I am able to access these flip-flops separately, okay, then we can probably go for an SRAM out here. Instead of these flip-flops, we could have an RAM. Okay, the RAM is again nothing but flip-flops only, right? So the advantage of RAM out here is all the outputs are again combined and taken as a single output, and we have a scan-in option also, similar to what we have. only thing is you have an address decoder. Okay, so there is a data line and there is an address decoder, and we using the address line we can put the data into the desired memory location. Okay, so in the entire flip-flop chain, instead of pure serial scanning, parallelly we can push in our required data to one of the RAM cells. Okay, so that helps in certain cases. Okay, so this is not generally done, but this is an option which is available. Okay, in certain cases where the testing requirements of each combinational logic is varied. Okay, so in that case you might want to have this kind of, okay, and this also need not be universal, right? It could be a mix of a scan and so in some part of the circuit, some of the flip-flops, if you want to have data, rest of them can be scan. Okay, so it can be a mix and match of a normal boundary scan and an RAM. For some flip-flops can be in the RAM configuration, so that we can independently access that. Okay, so that is all for today. So we'll stop it out here. In the next class we will talk about built-in tests. Okay, now all this test till now what we saw, it requires once the chip is fabricated, then we put it onto a test bed and then we do the testing, right? So but again this is a time consuming process, so you require an ATG machine which would generate the test patterns, and then you read the test patterns and then you compare with the results which is expected out of a fault free, all those things. But in the design, if we could incorporate within the chip something which can generate a test pattern, and not necessarily that for a particular block, right? I do so suppose this is one block. Okay, so not necessarily I do the testing of this block independently, this block independently, and take out the result and compare with a lookup table. Give one test vector here, then give the second test vector here, compare the result, third test vector, compare the result. So all those things will be time consuming. So in the built-in test you will see that a large number of test vectors is serially given, and all the output is combined into a signature, and you do a signature analysis. Okay, so all those things will be incorporated in the built-in test itself, right? So most of the chips will come as an built-in chip, especially if I talk about the but the once the when we are initializing a circuit, then the built-in test will run, and if there is a fault, because with aging also fault can happen, right? So it is not necessarily all this test, it is not a one-time test what we did till now here, post fabrication. But what happens with aging, right? When you are doing, and if you have made a chip, especially say in avionics, if you have an like a communication system or some radar system on an aircraft, right? Before you start flying the aircraft, you would want to do a full test of the system out here, because you can't afford that the system goes and fails in air and puts the life of the pilot and the aircraft into danger, right? So on the ground itself, when I'm powering on the system every day, every sortie, when I'm powering on the system, I would want the system to do a built-in test, okay, and tell me the system is okay, right? I may not be functionally using this at the ground, okay, just by when I'm doing the power. So there is a requirement that any VLSI chip or a PCB board, when I'm powering on, it should run a built-in test and tell me, okay, if this is fine, you could use it. Okay, so that kind of test. Okay, so this till now what we were talking about is post fabrication single test. Okay, but and obviously once it is fabricated and given on the air, suppose it is installed on an aircraft or in a car, I cannot put all the testers and do all this test what we are studied till now, right? So I can't remove the chip from the PCB and do the testing. So I have to have some test on the PCB itself every day when I'm using it. Okay, so that comes under built-in test. Okay, so that built-in test does that function. So it is another offshoot of the design for testability. So we'll talk about those schemes which are available in the next class. Okay, thanks a lot. We'll end it here for today.